So 4.5 billion years ago, rocky bodies and gas start to coalesce around a medium-sized star. And after 600 million years, planets emerge from the chaos. 1.4 billion kilometers from the sun, there's a massive, stormy, ringed planet called Saturn with dozens of moons. And from this vantage, there's another planet in the distance. This planet, it's Earth. It's 1.3 billion kilometers closer to the sun. It is a small, rocky, and blue planet with a single moon. And aside from the asteroids launched by interactions with Saturn's gravity, the Earth and Saturn are far enough apart not to concern each other, but one day their fates will meet. So on planet Earth, ages pass, life emerges, becomes really complex, and at 110 million years ago, that's 25 million years before the Tyrannosaurus rex terrorized the Earth, there was a dinosaur who lived near an ancient sea, which is now Alberta, Canada. And this dinosaur had a spiny back and a long tail. It's like an ankylosaur, if you've seen that, but with no club on its tail. It's called Borealopelta mark-mitchellii. It is a type of nodosaur named after the person who spent 7,000 hours chipping at a stone, basically. So the nodosaur lived its life, but one day it fell into a river and it was swept out to an ancient sea. Its body was bloated from having died. Its guts exploded out at sea and it sunk quickly to the bottom. It was covered in sediment and sealed in the earth. But due to the conditions of its entombment, the dinosaur quickly fossilized, and unlike many other dinosaurs, it wasn't flattened, but it was fossilized in 3D, and that's its stomach contents on the upper left, and fossilized skin included. So 110 million years later, humans have the tools and the will to unearth a fossil like this. Here's a segue. Also in the modern era, we also harness technology to shoot space probes around the solar system. And in this NASA video, the Cassini probe explores Saturn before its death. Also in the modern era, we created computers and smartphones on which we can tell stories about space and dinosaurs. Hi. I'm Brian Jacobs. I am a graphics editor at National Geographic. I create and envision interactive editorial features. I use code and design. Try to take science topics and make them approachable and usable to a general audience. And I'm going to talk about how I brought the nodosaur fossil and the exploration of Saturn via the Cassini probe to web browsers. And so what these two projects have in common, other than that intro, is using WebGL via Three.js for a 3D narrative presentation. And I'm going to talk more about the data and rendering techniques rather than the scrolly-telling aspects of this. So because this is a real three-dimensional fossil, not flattened like other dino fossils, we saw an opportunity to bring for digital to take this fossil, bring it into the browser, present readers with a 3D tour, and lead them through important features, and maybe try to see things that photography didn't afford us. So as the user scrolls down the page, we fly a virtual camera around a 3D textured models of the fossil. We're highlighting various features with annotations, changing the lighting along the way, and presenting readers with text from science writer Michael Greshko to explain the visuals, explain the science. So after the narrative, we also allow users to manipulate the model. This is using your kind of stock Three.js orbit controls. So how did we get this fossil into the browser? It starts with photogrammetry, or reality capture. So National Geographic fellow, Corey Jaskalski, he went up to the Royal Tyrrell Museum where this fossil is being displayed. But he saw it when it was still in its back room. He took thousands of of photos of the 6 individual pieces that comprise the fossil, and 6 pieces because during its excavation it basically burst. An unfortunate event, they didn't intend that to happen. So he has all of these photos. He actually took it in visible light, a normal camera, and a modified camera to capture UV light, which was kind of a novel approach but because it was a fossil like this, it might have had organic matter on the surface, and maybe we could see things in UV light that we couldn't see in visible light. So the general process, if you're not familiar with photogrammetry or reality capture, is that you take all of these overlapping photos, you feed it into the software, and the software basically creates a point cloud from all of the overlapping photos. It does an analysis of everything you feed into it, and a mistake in here, it creates a geometry, not a mesh. It creates a geometry which is like a tessellation of triangles. That's what you can generate from point cloud, and also you can generate textures, which are basically images. And from those, so basically, conceptually, that sounds sort of straightforward, like the software does the heavy lifting in terms of creating the model that you need. And then 3D graphics packages like Maya or programming tools like 3JS, WebGL, you can load the geometry into the browser, load the texture on top of them, add virtual lighting, add a camera, render a model, you have yourself an image. But the automation, bringing that into the browser, the automation part of making these models, it only goes so far. So photogrammetry, the results of it rarely comes out as a clean model. So a lot of time was spent cleaning up the model, cutting out the backgrounds. For instance, these fossil pieces were on giant pallets. So cutting out the pallets, basically. Cutting out the equipment that's in the restorator's room so we could spin this thing around in a black space. But most critically, optimizing the model in a responsible way. So simplifying or decimating the geometry in parts where it should be simplified. So for instance, the flat areas, you can have less triangles than the curved areas, and you'll preserve better detail that way, but have a smaller model to load into browsers. Corey Jaskalski, the photogrammetrist, if that's the word, his unoptimized data was 6 gigabytes, and what's in the browser is 15 megabytes. So that's about a 99% reduction in size, but not an extreme loss in quality. Definitely a loss in quality, but something we could deal with. All right, so this size reduction, this isn't a matter of pride, this was a necessity. Data limitations makes rendering real-time 3D objects in browsers pretty challenging. This is a screen grab from a talk from a game developer conference about Star Wars Battlefront. They talk about their photogrammetry process. There's a ton of photogrammetry in this game. And basically the gist is that it's rendering it in these environments, it's a series of tricks upon tricks to make you think you're looking at something more detailed than it is. And so the idea is to push as much detail you can while keeping things computationally viable. And this game, on a PlayStation 4, where there's beefy chips and gigabytes of data pre-downloaded at your disposal, is a different scene than a web browser with a data plan. So we don't have that luxury of preloading massive amounts of data in the browser. So I would argue it's even harder to do this stuff in the browser. We could argue about that. Okay. So basically, it just means that you need to kind of do even more tricks to render something fast and complex, but we can borrow tricks from the 3D gaming world. And one of these tricks is normal mapping, which I believe has been mentioned at previous OpenVis conferences in slightly different contexts. But here's the gist. Basically, you have your geometry, your tessellation of triangles. It forms a 3D surface. Each triangle has 3 vertices, and each of these vertices has a position in 3D space. So if you were to take a plane, so basically take the tangent of the curve, and overlay it on one of these vertices, take a line or a direction, a vector, and make it perpendicular to that plane, the orientation of that is called a surface normal. All right, so the key thing is you take all of the surface normals on a high polygon mesh, so something that hasn't been simplified. And all of those orientations have an XYZ. And you encode all of those XYZs into an image, into the RGB of an image. And it's basically called baking a normal map. There's a lot of jargon in the 3D world that I have run into, and it really helps to just like figure it out, because you can Google stuff. I mean, I'm sure you've all been there. Essentially, it's a data set in an image. So the left is a normal map, and the right is a texture map. And these two things correspond with each other, and this is the texture for the head of the notisaur. And so if you take, here's how to put it all together. You take a low polygon geometry, you bring that into the browser. And then you take the high resolution texture and a high resolution normal map. And the normal map lets us simulate detail via the interaction between the lighting in your scene and the orientation of the normals. All right, basically it lets you add shadow information and to simulate detail, because it takes all the orientations and it affects the lighting of the scene. So in the end, it's a huge reduction in model size and computation by not loading a complex geometry. On the left is, okay, you can kind of see it on this projector. On the left is without the normal map, on the right is with the normal map, and so you get enhanced detail. So the point of doing all this is because the initial prototypes of this project were convincing on desktop, but this was disastrous on phones. And so our users, it's a general audience, 60% of traffic roughly would be coming from phones, which is it really hurts me. But if performance isn't there, if the thing's jerky, if it takes forever to download, people aren't going to be able to use it. So it necessitated a lot of optimizations to be made. And so in doing graphics development like this, overcoming technical performance challenges, it's basically overcoming design flaws. So that's always in my head while I'm doing these projects. So figuring out how to do these kinds of techniques were crucial, but it's hard figuring out that stuff on deadline if you don't have a long runway. One thing that I didn't do that I would have loved to have time to figure out are kind of level of detail techniques, or LOD, another one of those terms. So based on how close or far you are from the object, you would load in higher resolution or lower resolution textures or lower resolution meshes kind of on demand as you need them. And this is what's happening in this Google Arts and Culture project. They do this 3D tour of some temples. And they're pulling off a lot of stuff in there. That's really impressive. So by doing something like this, it allows you to do things that are impossible with just preloading assets. I'm only rendering a single model, and that was 15 megabytes. So if with what I was trying to show. So if you imagine trying to render multiple archaeological sites, that's, I think, why Google took it where they did. This concept is also fundamental to 2D tile maps, like leaflet or mapbox. As you're zooming in, you're loading more data as you need it. And the company Cesium, they're extending this concept with 3D tiles, with kind of streaming 3D data on demand. 3D tile code isn't open source, but it does look promising. Just keep an eye on it. All right, so another project I'll talk to. I'm going to switch gears a little bit. I didn't solve render problems with techniques from 3D gaming, but I did so instead by being conscious of the balance between scale, rendering quality, and data accuracy. So Cassini is a space probe that had a planned demolition date of September 17th, 2017. It's dead. It is part of Saturn now, but during its life, it shot back incredible data that told us a lot of what we know about Saturn and its moons. And so to commemorate Cassini's destruction in Saturn's atmosphere, we wanted to show kind of a best-of gallery of what it captured and augment that with graphics. And by doing that, to show the orbiter's journey through 3D space and where it was during its travels, where it took the photos that it did, and kind of show its subjects as well in a 3D viz. So there is a legacy of interactive space trackers, notably the New York Times Curiosity Tracker by Jonathan Corm, Jeremy White. Really nice, extensive, it combines different types of media, and it updated as the mission progressed. There's the NASA Eyes desktop app, which really impressively simulates mission conditions and orientations. So like they got the exact orientation of their 3D scene that matched the photo on the right. Like that would have been cool if I could have done that. Okay, but relevant to this project, there's also this NASA data, which is lovingly called the ball of yarn. And so me and graphics editor Jason Treat, we knew this existed, and this represents the orbit of the various mission phases of Cassini and where it was in 3D space, in 3D outer space and in 3D space. And so how could we use this data to add context to the images Cassini took, show the breadth and complexity of the mission without overwhelming? So I'll get to that, but before I render Cassini's path, first I use similar data to render Saturn's system in 3D virtual space, Saturn and a subset of moons, and with Earth for scale. And then as you scroll down the page, we show how the mission progressed, and pausing the mission, where it took a photo. And that's also with text from Nadia Drake, science writer, expanding on the science we learned from these photos and from Cassini. And I'm showing the mobile thing because we had to get it working just as well on mobile. Again, a challenge with less powerful phones computationally than desktop. So unlike the Notisaur project, this isn't about textures of a single model except for Saturn itself, but it's about illustrating the trajectory of a point in space. So you'll see this represented as smooth curves of Cassini's path around Saturn. But if you looked at a glitched out version of this, you will see that the path can appear angular, and it even pierced the planet itself before its demise. So that's bad. That's not what I intended. But it kind of speaks to the heart of this project, which is using real NASA data, drawing thousands of XYZ positions where Cassini was at specific time increments, and connecting the dots and changing the opacity of these line segments as we progress in time, as we scroll down the page. So this type of data is called ephemeris data, and using the JPL Horizons system, I was able to download all of Cassini's locations over time. It's, I think it was 13 years of data in 3D coordinates, and coordinates relative to Saturn. So the Horizon system is really cool. It contains positions on hundreds of thousands of objects in our solar system, positions in the past, in the present, and projected into the future. And you can specify what you want these coordinates relative to. So in my case, it was relative to Saturn. You can do it relative to the sun, the moon, Earth, Mars, whatever you want in any of those hundreds of thousands of objects, I think. Or maybe only the big ones, the planets. So the big question was, how many positions per day did I want, down to very precise timestamps? And I downloaded this data for Cassini and all of the various moons, all the subjects of the photos that were being plotted. Throughout this project, I need to do sanity checks to make sure that I'm accurately representing what I'm downloading. So in this example, in the lower right image, from the perspective of Cassini, you can see Titan in the front and Tethys, the small moon right behind it, and they're in close alignment for the line of sight of the orbiter. But in the visualization on the left, you can see that there's like serious misalignment. And that was corrected by just understanding the granularity of the data that was needed. Because these moons move really fast. And if I don't have data down to the minute, kind of relative to the data that I have for Cassini, things would be misaligned. So I had to be careful to download high-res data where I needed it for the moons. And once I did have that, once I figured that out, that felt like a huge achievement. It was like just a weight off my shoulders because it was everything snapped into place. But I can't just download the data at maximum resolution for everywhere. It would crash browsers. So it was a balancing act. So similar to the case of the angularity of Cassini's pattern as it got close to Saturn. And the reason for that is that the orbiter moves super fast as it gets close to the planet. So if I didn't have enough data, if I didn't have enough time points as it was moving super fast, depending on the scale, you won't see it rendered as a smooth curve. So this is all to say that scientific accuracy is fundamental to my job, and taking great pains to, and I'm sure a lot of yours, but taking great pains to ensure that I'm not making egregious errors is super important. National Geographic has very high standards for visual fidelity. I don't want to sacrifice either if I can, but if something's got to go on deadline, it's not the science. So this morning, this was called contextual, not conceptual, but I think I was kind of in a bad mood. So I'm couching this a little bit. Okay, so if data visualization, if it's not providing accurate context or it has distracting artifacts, then why am I even making it? And this goes without saying for some here. I think that's like the main difference between data-driven news graphics, data art. There's conceptual consideration. There's aesthetics considerations for journalism. There's a big place for illustration and news. But this project specifically was not meant to be a conceptual expression. It was meant to add context and express knowledge about science. There's nothing wrong with conceptual, but that's just not what drives what I do day to day. So if the point isn't to be conceptual, I didn't want these projects to be a scrolling screensaver. I wanted to show features, key features, and the subjects using annotations. And legibility is fundamental to annotations. Apologies for the legibility on the screen. So there's no shortage of techniques to render text in a 3D scene. And this is kind of a repeat of what you heard earlier. Text can be rendered within 3D space. Kind of in this example, you can see that hello is blocked by the cube. World is in front of the cube. Hello is in perspective in the distance. And so basically objects can occlude each other. Another approach is objects can be extracted from a 3D scene. So basically you have XYZ positions within a 3D object, and you then project those positions onto a 2D plane. So kind of your viewport, you take kind of an XY position where it is within a browser window. And then you relay those positions to HTML elements or SVG elements. So the downside of HTML for positioning labels and overlays is that you don't get this occlusion automatically. So if you're pointing at a dino face, we rotate to the back of the head, the label should disappear. The plus side, though, is that you get so much for free. You get search engine indexable text, you get web fonts, you get media queries for responsive changes, and fundamentally browsers are meant to render text, and so you get the legibility that browsers naturally afford. And that was the approach that I went with these projects. This is kind of this is just a keynote example, but so this project I use HTML for the text, SVG for the D3 via D3 for the lines. For Cassini, I use the D3 annotation library by Susie Liu, which I think she presented at one of these conferences. Is that true? Okay. Which was pretty great for most of my needs. I'm not going to go too deeply here, but other considerations for 3D web projects are how to deal with responsiveness. There's no such thing as 3D media queries, so how you handle things, morph across screens, how things fit within a bounding box is the question. So in both of these projects, there's a camera moving through 3D space that's scroll triggered, has these stopping points. And at each of these stopping points, basically make the browser fit one of these spheres within the field of view of the camera. So basically, if you can fit the sphere and you can fit your object into the sphere, then it'll be responsive. Okay. So I don't really release code bases necessarily, but I do try to give back, and there's more detail on these techniques and thought processes behind these. More the how than the why, a little bit of the why. In articles that I wrote, technical and design considerations. So check these out if you're interested in a little more of a deep dive. And thank you for listening. If you want to visit any of these, links on the left, resources in the middle about how to construct something like this, and the tools I used on the right, and a lot of credits for these slides, and you can download the slides, so don't worry about taking pictures. I have 4 minutes left. Went fast. If anybody has any questions, are we taking questions?